So in this section, what we're looking at is the near-Earth approximation. And one of the things we really need to keep in mind is, what does that distance r refer to in the gravitational equation? And what I mean is, we're looking at the magnitude of F. We've got g m1 m2 over r squared. So this distance is actually center to center. The reason being, for a large extended object, from the standpoint of gravity, we can assume that all of the mass is acting as if it's concentrated right at the center. This has to do with the spherical symmetry of the object, and when we're dealing with non-spherical objects, it's a good approximation. So this distance r is always going to be center to center. So if you're looking at the strength of gravity above the surface of the Earth, you've got to include the radius of the Earth in your calculations. So if we're looking at an object a height y above the Earth, then here is the magnitude of the gravitational force. We've got the radius of the Earth plus y is the radius that we have in the equation down here. Now, why exactly does this near-Earth approximation work? You've probably seen this if you've taken physics before. F is equal to mg. And that's the near-Earth approximation. The reason that we can get away with this is if you look at this term right here, this is just a 1 over r squared term. So if y is much, much smaller than the radius of the Earth, then we can assume that this quantity is approximately just 1 over the radius of the Earth. And the radius of the Earth is approximately 6.4 times 10 to the 6 meters. So anything that's significantly less than that. And by significantly less, we can say anything that appears in this next decimal place. So this 4 appears in the 10 to the 5th meter range. So 10 to the 4, anything that's less than or equal to 10 to the 4 meters, or about 10 kilometers, can be assumed as being within near Earth. Once you get outside the 10-kilometer range, then you're going to have to take into account the fact that gravity is dropping off. So to come up with this F equals mg from this big equation, what we do is just combine these factors right here. Again, let me write this down, that F is equal to g m e times m over r squared. All we've done is take this mass out and realize that all of these terms right here are more or less constant for that near-Earth approximation. And so when we calculate that value, we find that this has some value about 9.8 newtons per kilogram. And so that is the near-Earth gravitational field, or little g. It is sometimes incorrectly referred to as the acceleration due to gravity, and that's due in part to the fact that it has units of acceleration. A newton per kilogram is also equal to a meter per second squared, the units of acceleration. But that's not a very accurate statement. So hopefully this overview will help you a little bit.